We are here with Raffaello D'Andrea. He's professor for dynamic systems and control at the ETH Zurich. He does some very cool stuff. Welcome to the ZURICH.MINDS show.
Thanks a lot, Rolf. It's good to be here.
What do you do?
What do? I like to create things that have never been created before. Things that move, things like robots, autonomous systems, things that learn, things that adapt.
So when you say you're professor of dynamic systems and control, what does that mean?
Right.
It kind of sounds abstract.
Yeah, it sounds a little bit abstract, but it's actually pretty easy to explain. So, I'm interested in things that move. So part of it is dynamics. Dynamics is the science of understanding how things move, the science of motion. Once you understand them, then the second part is what do you do with that knowledge? And that's the control part. So once you understand it, you can figure out how is it that you can manipulate it? How is it that you can affect its behavior such that it does what you want it to do? A robot is a good example.
Okay, so you design robots, but you also design other stuff.
That's right. A lot of it tends to be robots, but it's the whole system that I'm really interested in. How do you design the system that includes the robots, for example?
Okay, let's take an example. We have a couple of things here that you've worked on. On which part could you explain this the best?
Probably let's start with the most tangible example. I know these don't look like robots, but they're actually little toy models of it. So there's this company, Kiva Systems, of which I'm a co-founder. And the idea there is to use hundreds of mobile robots. They look like this. They're larger. They're about a meter in diameter. That run around a warehouse. They pick up inventory all over the warehouse. So imagine thousands of things like this. They pick them up and then they bring them to the perimeter of the warehouse where people are picking things off of these shelves and filling orders. So instead of people walking around the warehouse, which is inefficient, people get tired, prone to errors, etc., we have this fleet of mobile robots. Largest warehouse we have is about 1,000 of them that move all of this stuff around, and the people are then picking it.
So it picks this thing up, kind of moves it over, then people pick the shelves, then another robot comes in and moves it over here.
That's right. So there would be a person, and they would be, there would be 5 or 6 of these robots in a queue. So this person would basically pick something, scan it, put it in a box, and by the time they turn around, that robot is gone, and there's a new one with more stuff to pick. Mm-hmm. So that's an example of the overall system. How do you design a system that does this? Part of it includes these little mobile robots that have to drive around without hitting each other, etc.
Mm-hmm. Let's take another one. That's very cool. Why don't we take? You started off in your previous life, with the Robocup.
That's right.
So this is. What does that do?
Yeah, so this was a program that I ran at Cornell University. I was a professor there for 10 years. We competed in this international competition called Robocup. The idea there is to field a team of autonomous robots, up to 5 per team, that could play against other teams from all over the world in a game of robot soccer. So these guys played soccer. So they drove around, they had little kicking mechanisms. They could even dribble the ball by spinning it backwards. And what they would do is they would find their teammates, go around opponents, pass the ball to them, and they would, basically play a game of soccer. And it was fully autonomous. Mm-hmm.
And you won that Robocup?
Right. We won it 4 times.
4 times?
Yeah, from 1999 to 2005, and then we stopped competing. So it was a great experience. Had phenomenal students working on it. Bachelor students, master students, PhD students, postdocs. It was really a big team effort. Computer science, electrical engineering, mechanical engineering. Just a great systems project.
And why did you stop?
So a couple of reasons. One is that's the time that I was doing Kiva. So I basically went on leave and I was doing my sabbatical at the time.
That is what we just
talked about. That was the first part of it. The second one is that, the exciting part of the competition, I think all the best years were behind it. The solutions were tending to asymptote to the same design, basically. When we showed up in 2005, all the robots pretty much looked like ours, right? So there wasn't as much innovation in the system aspect of it, which is what really interests me the most.
What I really like is the one that plays badminton here.
Right.
Why don't you tell us about this?
Right. So this is
a flying thing.
Right. This is something that we've done very recently with the group that we have here at ETH. So the idea here is that we have this thing called a quadrocopter. It has these 4 propellers with 4 motors here, and by controlling their relative speed, you can make this thing go up and down, roll, pitch, yaw. It can do some very aggressive maneuvers. It's very acrobatic. One of the tasks that we set ourselves out to do, again, our objective is to make systems make them do things that have never been done before, to push the boundary of dynamics and control. So we thought, well, what if we could design a system that allowed us to throw a ball up in the air and then have these things play ping pong or badminton with each other, hit the ball back and forth. So we've actually completed this system. There's a lot more that needs to be done. The system can learn and adapt, but we want to make it perform much, much better. Yeah, so that's what this thing does. It's on the web. You can get videos and stuff.
What was the most difficult part of this? I mean, you can buy this is purchased, right? These systems. Right. So what you did, you basically did the software.
Exactly. So the system design. So there's really two parts to all of these systems. The first part is the architecture. How do you architect the system? How do you figure out what part does what? Where do you put the sensors? Where do you put the actuators? What information is shared? That's the architecture. And then there's the algorithm part. Once you have that information and you have it, compartmentalized, how do you actually take that information and do something interesting with it so that you can command things properly and it doesn't go unstable, it doesn't go out of control. So we did both. We architected the system. We had to figure out, where are we going to put the sensors, the actuators, how much information do we send this vehicle, etc. And then, of course, once we did that, we had to develop the algorithms to do things like intercept where the ball is, predict where it's going to be, try to intercept it. How do I hit it such that my friend can have a good chance of hitting it back? And all of this is done, while flying. I mean, it's not only is it difficult for these things to fly, but they also have to fly around and intercept, a ball, which is, a challenging task.
You mentioned something about learning systems. They learn.
Right.
What exactly do they learn? Isn't it just all programmed in there?
So, yeah, it's a good point. Just because something is programmed in there doesn't mean that they're not learning, right? So, for example, they could learn a model. As I mentioned earlier that we do model-based control. We try to understand the dynamics of the system, but you can never understand them perfectly. Okay? You can sit and read books all day and write a whole bunch of equations. At the end of the day, you have to do some experiments to validate your models. So we do validation while we're actually operating. So while these things are flying around, we're updating our knowledge of what this thing really is actually capable of doing, and we change our strategy based on that knowledge. Now, that is programmed ahead of time, but it still doesn't mean that it's not learning, right? Mm-hmm. The learning is programmed ahead of time. How it learns is programmed ahead of time. But what it actually learns, it's not. It has to do experiments to learn it.
Mm-hmm. So theoretically, it has to be here, but then you see it should actually be over here. So it learns that difference. It kind of moves then over. For that
as an example.
As an example.
That would be an example, right? But of course, it has to do a whole bunch of other things because it's, this is an unstable vehicle. Mm-hmm. So it also has to figure out, if it keeps on going to the left all the time, sure, it has to go to the right, but that's simple to say. This thing is moving really fast. So how does it actually move to a little bit over without going unstable at the right orientation, etc.?
Now, somebody might say, okay, this is all nice and good. You're having a fun time here with your team.
I am.
And you probably do. What does society get out of this?
Right. So I think, it's great that we talked about those projects in the order that we did. Kiva Systems, it's clear that it has, an impact. The company's pretty big now. It's about 300 people. There's installations all over the world. So that's a tangible example of the technology. But how do we get to there? It was interesting. It actually came from robot soccer. The way the company got started was Mick Mounts. He had this brilliant idea. He's the founder of the company. Of using robots in distribution facilities. But of course, then you have to find people to actually make it happen. So that's when we met, and the reason we met is because he was using our Robocup videos that were on the website to convince investors that that technology is available. So then we teamed up, and a lot of the know-how that I learned from doing robot soccer carried over directly to Kiva Systems. A lot of my former students work for Kiva Systems. And when we were doing Robocup, we had no clue about distribution facilities, right? So the point is, to me, universities are a place where you should be unconstrained. You should be pushing the boundary. You should really, again, try to do things that have never been done before, such as a vehicle hitting a badminton ball back and forth to each other, because things will come out of it, right? It's basically a faith that I have that if you're pushing the boundary, if you're doing these things, somebody, an entrepreneur, will get ideas of, wow, if they can do this, then maybe they can do this as well. And in fact, we are talking to several people about flying cameras.
Flying cameras or laying brick walls.
Oh, that's right. That's another cool project that I have going with it. Right. So we're working with architects at ETH, Gramazio and Kohler. They're world renowned for using robotics to build structures. And in particular, one of the things that they do is they use robot arms to build brick walls. And these brick walls are not just your standard, flat brick wall. They have these beautiful shapes that would be impossible for a person to mimic. It needs the precision of a robot arm in order to realize. So we kind of wanted to push that to the next level. So we've decided to do this installation where we're going to build a 6-meter tall structure, about 3 to 4 meters in diameter, with 1,200 of these bricks. But they're going to be assembled by our flying vehicles.
Wow.
So fully autonomous, no humans controlling it. Basically, once these things start, they're going to pick up the brick, fly around, put it in the right spot, have other ones doing it all concurrently, and we're going to show that in Paris in December.
And eventually, I mean, we could imagine that buildings are built that way.
Right.
You'll have an army of these autonomous vehicles, and you press the button, they start taking off, and they build the building.
Right, and that's a long ways away, but there's a lot of things in between that would be very useful. Semi-autonomous, where a person is still coordinating, but these autonomous machines help them in the process. Mm-hmm. That could happen. This is basically a futuristic view on things. So, we don't mind speculating. It's not that we think that buildings are going to be built exactly in this way, but that's not the point. We want people to start thinking, what could be done. And, this is an exercise in what could happen in the future.
When you talk about these autonomous systems, especially these flying vehicles here, fear gets into my bones, because any terrorist could say, okay, I'm kind of building a small little vehicle or an army of these little things with little explosives and fly to some city and or even houses and let it explode.
That's right.
Could that happen?
Yeah, I actually think it could happen. Basically, the technology that goes into doing something like this is becoming readily available. The parts, for example, these are off-the-shelf propellers, motors. There's a company that makes these frames, and they also make the electronics. We use our own electronics because we want to have more control of how these things fly. But you can buy off-the-shelf electronics. You can buy GPS receivers for very low amount. Computer vision is becoming better and better. So you can put cameras on here that can do things like do obstacle avoidance, avoid walls, etc. This is, out there, and there's no reason why, say, within 5 years, 10 years, a hobbyist could not assemble something like this. Thousands of hobbyists assemble things like this and coordinate them to do something. If you think of nefarious uses, you can imagine them putting things like explosives on them and having them coordinate their motion and at a stadium, or So this is definitely possible. It's definitely, the technology is definitely going to allow people to use it in detrimental ways.
Yeah, and we can't do anything about it.
I don't think we can. I think trying to suppress the technology, it's just not going to work. I mean, you can't, right? It's in our nature to want to build new things. I think we just have to recognize that. By suppressing it, I think you're only going to make the problem worse. I think the best strategy is the complete opposite. Make it open. Make everything readily available, and really try to understand the underlying causes of why people would want to do this, and recognize that it is unavoidable that people will use the technology in negative ways, but suppressing it is not the answer.
Let's talk about something else that's very nice.
Fun.
This is what is this? This is a flying array.
That's right. This is one module of the distributed flight array.
Okay, flight array.
Yeah.
What does it do and how does it work?
Right. So the idea here is that...
Maybe we have to kind of show it here.
Sure.
That's kind of a one of those models here.
Yeah, exactly. Okay. So this is one of the modules. It can do two things. It can drive around. It has these wheels. right here. So if I turn it around, you can see them a little bit better. They're called omnidirectional wheels because they allow the device to drive in any direction at any time. It's not like a regular car. It has wheels and it has a propeller. So it can do two things. It can drive on the ground and it can produce thrust. But on its own, it's only one propeller. It's completely unstable, right? So what can happen is that we have multiple of these modules. They drive around on the ground, they find each other, they interlock, they have these magnets here that allow them to do that. Then they start coordinating their motion, they find their friends, and once there's enough of them, at least 4, they communicate via these infrared transmitters, receivers. That allows them to basically figure out how should we work together to fly. And that's what they do next. They control their propellers, the whole thing takes flight, it can fly around, and it can fall apart in the air, fall to the ground, and the whole process repeat itself.
And do you already see some sort of an application for that, or that's pure basic research?
That's pure basic research, because in order to do this, there's so many interesting problems that need to be solved. I'll just pick one of them, for example, the coordination of flight. You know, you have all of these different thrust-producing devices in all these different configurations. How do you come up with a control system that no matter how these things are oriented will fly reliably, will do what you want it to do? How do these things communicate? What should they communicate in order to optimally fly so that they don't break apart, for example, which would have the physical interpretation of how do you reduce stresses in a structure, for example, such as this.
Yeah, go ahead.
Well, I was going to say what's interesting is that even though this has absolutely no utilitarian value. When people found out we were doing this kind of stuff, an entrepreneur came to our lab and he ended up hiring 2 of our folks that were postdocs at the time in his company. And what the company was doing is using high altitude wind turbines for energy generation. And if you looked at what their turbines were, it wasn't just one, it was basically an array of turbines that they would turn into the wind, right? So, you know, again, you can see the similarities. We were never thinking that, but again, it's serendipity.
Yeah. What is the coolest thing you could imagine building in the next 5 to 10 years? I'm sure you have thousands of ideas and sketches and notes. And what would you love to build, or what are you going to build in the next 5 to 10 years?
Yeah, I'll say something maybe a little bit shorter term, because I have a PhD student that's just starting on this problem. What I would love to make is a deformable surface that can adapt in real time, that can be controlled in real time. So imagine this table, instead of it being a table, all of a sudden it could basically rise up in different spots. You could create a little city that was changing. You could create a face that was talking. Basically a real-time deformable surface. I have this in my head. I've been wanting to do this for a long time, and so we're actually starting to do this project.
Okay, cool.
Yeah.
I mean, pardon that comparison, but it seems like a little boy. You know, you have these toys, and you can just do whatever you want to do in your lab.
That's right.
What makes you tick?
What makes me tick? Yeah, I don't know. Let me just say though that you know, even though it looks like we're having fun, we are. You know, we still publish our results in top journals. You know, this work was one of the 4 finalists at the ICRA Robotics conference. You know, top 4 out of 1,000 papers. So, you know, the community recognizes the innovation that's going on here. We have another project, the Balancing Cube, which was won a best paper out of 450 papers. So we are having fun, but we're also pushing the boundary of research. And to me, that's exciting, the fact that we are contributing to knowledge. I think ultimately what makes me tick is, in terms of just the pure technology aspect of it, I just love to create. I love to make things. I always have, and especially things that have never been built before. It just gives me so much pleasure to create things.
Now you are active in the science field with this research. You publish your papers. You solve these problems of control. You, as we saw with Kiva Systems, you're also an entrepreneur. You use that to build companies, and then you're also active in the arts field.
Right.
how come you're so active in so many different fields? Is it just one big field, or is it different fields?
For me, it's the same. Okay. For me, there's absolutely no difference. So, you know, I've collaborated with artists before. We have 2 pieces in the National Gallery of Canada. One is called the robotic chair. It's a device that, it's an everyday looking chair that falls apart into 6 pieces, the 4 legs, the base and the back. And then the base proceeds to find all its pieces. It climbs over the legs if it has to. It finds all the pieces, it reattaches them, and then the whole thing goes back up, falls apart, and the whole process repeats itself. We have another project called the table. You know, to me, it's all the same, right? We're building really interesting stuff. We're kind of pushing the boundary of what autonomous systems can do. They are artistic in many ways. You know, there's a certain elegance to being able to do this in a nice way. If you see these things fly, we have another project where we have, you know, these vehicles that are dancing to music, choreographed to music. I think it's inevitable that we tend to, you know, project aesthetics into these robots. To me, they're all the same. You know, Kiva Systems, you know, it's a successful company, but what always motivated me was the ability to, you know, to help create a system where we have thousands of these mobile robots moving around. That was the mental image that I had, and doing a company is the best way to actually realize that.
Great. Well, thanks so much for talking to us, and
good luck on your research.
Yeah, thanks for having me.
Thanks so much.